Very exciting. We have our last lecture, last bit of new content of the semester coming up, of the year really, of organic chemistry. After today, we won't have any new lecture material to work on. Next class period is of course going to be that optional makeup exam for exam 3. That next week we'll have our 4th exam. The Tuesday of next week, or Monday of next week, we'll just do a review session of this last unit's material, all right? And then we have a week between a week before our final exam week where we'll spend doing just some review. So a bunch of full semester review. Our ACS exam is a full semester, full course ACS exam. So there's a lot of stuff from that first semester that I think we haven't thought of in a while, like cyclohexane chair structures, stuff like that. That's not too bad, but we just need to make sure to remember it, go review it, stuff that at this point, given how much everybody knows, I don't think is too bad, as long as you just remember to spend some time thinking about it. All right, so again, we got just one more set of lectures to go here, one more lecture to go, and we're going to talk about reactions of amines. All right, so first of all, one that we had already talked about, spend some time talking about, but really, really important for these functional groups are these acid-base reactions. All right, so amines are good bases. Okay, so if we have our amine in the presence of any sort of an acidic functional group, so for example, a carboxylic acid, okay, everybody take a second, and what would my products be? All right, so if the amine is a base, that means it accepts that proton, giving it a positive charge. And my carboxylic acid becomes that carboxylate ion after getting deprotonated. All right, so important to keep in mind because this one right here is not one of those carboxylic acid derivative conversions. It's a lot of converting between different carboxylic acid derivatives. And it would be tempting to say, oh, we make an amide here, but that's not the case. Instead, we have an acid-base reaction because those amines are basic. All right. Amines are good bases, but they're also good nucleophiles. And that's what we're going to see kind of in a lot of the cases here. So first of all, let's take an amine. Okay, so now if we add in an alkyl halide, everybody take a second and predict our products here. All right, remember alkyl halides are good electrophiles, so that lone pair on that nitrogen can attack that electrophilic carbon and kick off that iodide leaving group. Okay, so if we draw our product of this first step here, okay, importantly though, this thing is also an amine. So it can also react with alkyl halides, or with our iodoethane in this case. So you're going to get a mixture of a bunch of different products. There's no way to stop it after just one addition. All right, so you'll get a mixture of all these different amines. It's just going to react over and over again. All right, so we have our tertiary amine. But this tertiary amine also has this lone pair on there. All right, so we can also get what's called a quaternary amine salt, where that nitrogen again plays the role of a nucleophile. But now we have a nitrogen with 4 bonds and no lone pairs. So it's going to have a positive formal charge, which will be counteracted by that leaving group iodide's negative charge. Okay, again, what we call a quaternary aminium salt with that nitrogen with that positive charge. What's up?
For the first two,
Uh-huh.
would that be under acidic conditions?
These would be these neutral conditions. You don't need to have it be highly acidic. You actually can't have it be acidic, or it would protonate that amine. But you don't need to have a base catalyst either. They will react under just neutral conditions. Okay, so we're going to take advantage of this here, this formation of this quaternary aminium salt in what's called a Hofmann elimination. Okay, so first of all, on elimination, what do we think our product is going to be of this elimination reaction? An alkene. All right, but the problem with these elimination reactions, similar to what we had with our alcohols, is this amine group is a terrible leaving group. It's even worse than an OH group as far as the leaving groups go. So just like we did when we were talking about alcohols, we need to use this strategy of turning it into a better leaving group, and that's going to be by creating one of those quaternary ammonium salts. So what we're going to do is put in a big excess of iodomethane. A very small alkyl halide here, just a methyl group. We're going to use the iodine compound because the iodide is the best leaving group of all the halogens. So it'll just really efficiently form that quaternary ammonium salt. All right, so we'll stick 3 methyl groups on that nitrogen. And since it's got a positive charge, it's got that iodide counterion. Bless you. All right, more common is to see this sort of summarized. CH3, 3 plus over here, minus over there. All right, so we made that quaternary aminium ion here, and now this is a good leaving group. All right, so now we have a good leaving group. If we have something that's a good base in there, we'll create an alkene. They use something kind of fancy here. They use this silver 1 oxide, all right, which really just creates hydroxide in solution, but in a way that it's only going to be a base. There's no nucleophile, so there's no substitution side product. Okay, so we can just say this right here will create OH minus, but only as a base, not a nucleophile. All right, so we're going to get an alkene product. However, interestingly, that alkene, that double bond is going to form on the end of our molecule here instead of that more stable alkene, which would form in the middle of our molecule. Okay? So if we look at our mechanism here, okay, we have that quaternary ammonium salt. I'm going to draw it out here with its 3 methyl groups to make a point. Okay, so remember, in an elimination reaction, it's the hydrogens on the neighboring carbon that need to be removed at the same time as that leaving group is kicked off. All right, the special thing about this leaving group here, or the special consideration here, is that it's massive. It's this nitrogen with these 3 methyl groups on there. It's an extra large leaving group here. So if we look at our neighboring carbons, one of these is a secondary carbon. The other one is a primary carbon. And the primary carbon has those hydrogens that are much more accessible. Those secondary hydrogens are kind of buried and sterically hindered by that big leaving group. Okay, so it turns out that our more accessible hydrogens are the ones that are going to be removed in this reaction. All right, so I'll just kind of copy and paste below here so that we can see it without all those markings. All right, but again, if we're going to do our mechanism here, we're going to have some base. And again, even though we use that silver 1 oxide, that silver oxide, it's really just hydroxide playing the role of our base. All right. These are what we called E2 elimination mechanisms, which is when your leaving group leaves at the exact same time that your base is removing that hydrogen. So everything here happens in one step. Our base grabs that hydrogen, that pair of electrons comes back down to reform that double bond, or to form that double bond, and we kick off that amine leaving group. All right, so the result is that our product is that less substituted alkene. And then our leaving group was that trimethylamine. Now it doesn't have the positive charge because it accepted that pair of electrons when it acted as the leaving group. All right, so then keeping this in mind, let's take a look at another amine, see if we can't predict what the alkene product would be of this Hofmann elimination. Oh, whoops, I mixed that up. That's the second step. All right, so importantly, what are we going to have at step 1 here? We're going to have that quaternary aminium ion. So now my nitrogen is fully decorated with alkyl groups. So I got to put 2 new methyl groups on there, giving it that positive charge. And so it's got that counter ion, that iodide ion. All right, so now after step 2, what will my product be? Okay, so we got to figure out where our elimination is going to occur here. I'm going to get rid of this iodide ion just because it's cluttering things up here. So first of all, can't be these 2 methyl groups, right? They're too small. So I'm not looking at the carbon that's attached to the nitrogen. I'm looking at its next door neighbors. All right, so these are these 3 carbons I'm going to look at to decide which one is going to be my elimination, contain my elimination hydrogen here. So I'm going to look through this first one up here. This is a primary carbon. If I go down here, this is a secondary carbon. If I go over here, this one's a tertiary carbon. All right, so which one am I going to remove a hydrogen from? The primary, the most accessible carbon is the one that loses its hydrogen. All right, so to be clear, here's my hydrogen. When this base comes along and grabs it, it's going to kick off that leaving group. So my alkene here will actually just be this small 2-carbon ethene ethylene, no, ethene, sorry. And my other product will now be this tertiary amine. Where now my nitrogen, because of that first step, has these two methyl groups on there. All right, so again, we're not looking at the carbon attached to the nitrogen. We're looking at their next door neighbors and comparing their classification, primary, secondary, or tertiary. All right. Yeah.
Does this ever happen on a secondary carbon?
If that was the most accessible one, yeah, like if there wasn't a primary carbon there. In general, then that reaction would be slower because you'd have to wait for that secondary carbon to be deprotonated, which would take longer, but yes, it would still occur. All right, so one of our benzene derivatives that we learned about contained that amine group. And it had a fancy name. This is aniline. And that amine group on there was was one of the most activating of all of those functional groups on there, right? You had a lone pair located directly next to the ring here. That lone pair can be added to that ring, making it an even better nucleophile. So this is one of our strongest to that electrophilic aromatic substitution reaction. All right, so much so that if you added bromine to this without any catalyst, we talked about how we always needed that catalyst in these benzene, these electrophilic aromatic substitution reactions. In this case, if you add in bromine without a catalyst and you keep this thing really cold, it'll still react completely with that ring. You will brominate all of your ortho and para positions. All right, we cannot isolate the monobrominated product. All right. Another problem with aniline in these electrophilic aromatic substitution reactions is you can't do any Friedel-Crafts reaction with an aniline. There were a few groups that tried, and it was really confusing because you got this salt product out of it. You got a solid precipitate that happened, and then you analyze your product and you still just have aniline. The problem is that aluminum chloride catalyst will also accept that pair of electrons, and you just get this aniline salt. Forms a complex with that aluminum chloride. So no Friedel-Crafts reactions. right, so you just got to be a little clever. You can still do this here. You just got to add this intermediate step. Okay. So this would be what we would call a protecting group. All right, let's think back to our carboxylic acid derivative conversions here. What would happen if I took aniline and mixed it in with one of those more reactive acid anhydrides? Right, we can convert from these less reactive to these, from these more reactive to these less reactive functional groups. All right, so what we would get is this amide. All right, and as we discussed with amides, this lone pair right here is preoccupied with that neighboring carbonyl group, right? This lone pair is being bounced up to that oxygen right there. So these amide nitrogens are not as good of bases or nucleophiles. And importantly, this is not a strongly activated ring. So if we take this guy and we do one of those nucleophilic aromatic substitution reactions, we're just going to keep our same conditions before. I actually don't think you need the catalyst, but let's just not overcomplicate things. You will get that electrophilic aromatic substitution product. You will get predominantly the para product because you put that big bulky group on that nitrogen, kind of blocks up that ortho position there. All right, but importantly, a protecting group is only good if we can get rid of it. All right, and so we have a way of converting from amides back to amines using just aqueous basic conditions. Oh, whoops, I forgot a hydrogen over here. All right, what is my other product here at this step? Like this is this part. No. The leaving group, and what is it going to be here? All right, so remember, this is taking advantage of the fact that under acidic or basic aqueous conditions, an amide will be converted into a carboxylic acid and an amine. Under basic conditions, it's that carboxylate ion. So one of our carboxylic acid derivative reactions here. Okay, so my other product up here would be that acetate ion. All right, but importantly, if we want to do a electrophilic aromatic substitution reaction of an amine, we're going to first create it into, turn it into an amide using one of our more reactive carboxylic acid derivatives. So like an acyl chloride or an acid anhydride would work great. Then that creates a ring that is no longer as strongly activated, so we would just get that mono-substituted product, and then we could convert that amide back to our amine using basic conditions, using a basic aqueous solution. All right. That clock is very wrong. Okay. So the other thing, sticking on these aniline topics here, reactions of anilines. We can also do these nucleophilic aromatic substitution reactions. Where we're going to take our aniline and we have some nucleophile, and we're going to swap out that aniline, with that amine group rather, in aniline for whatever that nucleophile is. All right, so in order to do that, again, that NH2 is not a good leaving group, so we have to convert it into a good leaving group. And what we're going to use is nitrous acid and sulfuric acid. And what that first step is going to do is turn that into a good leaving group. By creating what's called a diazium salt. Oh, I'm sorry, diazonium. All right, then we'll follow it up in a second step with that nucleophile, and we will get that substitution. All right. When we perform this second step here, what is our leaving group going to be? Our nucleophile is going to attack and kick off that leaving group. So what's going to leave? It's just nitrogen gas. Super duper, ridiculously stable, ridiculously entropically favorable, just about the best leaving group that you could possibly have. All right, we don't really see substitution reactions very often, these nucleophilic substitution reactions. Before, when we learned about them, we had like these really stringent conditions about there being deactivators on the ring and stuff like that. But this creates just this ridiculously good leaving group here that can be swapped out for the nucleophile. All right, so for aniline, we got these electrophilic aromatic substitution reactions, where in order to accomplish them, we're first going to convert that amine into an amide, and then we can take it back off at the end. Or we can substitute out that aniline using these diazonium salt methods here. Okay, all right, so then the last thing that we're going to talk about here are what are called heterocyclic amines. We talked about these a little bit when we were talking about aromaticity, and there's two big ones that we want to know here, two special name compounds here. And we want to understand the features of these compounds here. So the first one, these are all going to be rings where nitrogen is a member of that ring. So the first is the 5-membered ring. All right, this one has the special name here, pyrrole, with 2 R's. All right, the last one, the next one is our 6-membered ring, heterocyclic compound. And this one's name is pyridine. Pyridine was everyone's favorite compound to work with in the lab, and actually all amines have a tendency to smell like fish. Like amines are not the really pretty smelling compounds that you like, not like esters, which have a tendency to smell very good. Amines are always pretty stinky. All right. Okay, so importantly, these are both considered to be aromatic rings. If we go through and count, in each of these we have an odd number of electron pairs contributing to these rings. So nice stable molecules, but they have very different properties. All right, for pyrrole, in order to get you to that 6, that odd number of electron pairs, you have to count the lone pair on that nitrogen. All right, so in pyrrole, that lone pair is already doing something. It's already preoccupied. It's being delocalized around that ring. Which means that pyrrole is not going to be basic, and it's not going to have that nucleophilic oxygen. Nucleophilic nitrogen. All right, instead, pyrrole is going to behave a lot like an activated benzene ring, and it'll undergo those electrophilic aromatic substitution reactions. So instead, it will undergo electrophilic aromatic substitution. All right. Pyridine. If we look at its ring, the 1, 2, 3 odd pairs, the odd number of electron pairs that are delocalized around that ring are all those pi bonds. So in this case, this lone pair is not participating in that delocalization around the ring. All right, so then pyridine is basic. And kind of meh nucleophile. You don't really see it play the role of a nucleophile very often, but you do see it play the role of a base quite a lot. All right, instead, it's not contributing to the electron density of the ring. Instead, that nitrogen is the most electronegative member of that ring. So through induction, it's kind of hoarding some of that electron density. So because of that, these do not undergo electrophilic aromatic substitution. So not EAS. You still see pyridine a lot in organic chemistry, but it's almost always used as a solvent. It's a good solvent. It's a liquid at room temperature. And if you do need something that's going to play the role of a base in your reaction, if you need something to accept a proton at any point in your reaction, using a solvent that can do it is a great sort of way around here. So where we usually see pyridine is as a basic solvent. Basic nonpolar solvent, which is kind of a hard needle to thread. All right, so then if pyrrole, we'll say it does undergo these electrophilic aromatic substitution reactions. Let's do one of those here. All right, and let's remember in these electrophilic aromatic substitution reactions, the ring is playing the role of the nucleophile, grabbing onto whatever your electrophile is. Let's just leave that as generic. Well, fine, that's fine. All right, but let's see, there's two possible, if my nitrogen, if I'm starting to number away from my ring here, I can either have carbon 1 or carbon 2 with that new electrophile on there. All right, and let's see if we can't figure out which one it's going to go on here. Okay, so remember there are already hydrogens on each one of these carbons, just one. So let's explicitly draw in our hydrogens here. So if I broke that double bond in order to add that bromine onto carbon 1, what am I going to need to place on carbon 2? It got that lone pair of electrons taken away from it. Not that lone pair, I'm sorry, that pi bonding pair of electrons taken away from it. It's going to be a carbocation. All right, likewise, if instead I were to take that halogen and put it on carbon 2, that means carbon 1 has to be my carbocation. All right, so I want you guys to draw our resonance contributors here and see if we can't determine which one of these is going to be the correct place to put this bromine, carbon 1 or carbon 2. All right, so in my first structure, I have this allylic positive charge. Okay, so that can accept that pair of pi electrons. And bounce that double bond over here. And now we have a positive charge over here on this carbon. Now, is there another resonance contributor I can draw? So now I have a different pattern to spy here, but I do have a lone pair located right next to that positive charge. And so that lone pair can attack that carbocation, giving me my other resonance contributor, which is going to have a double bond on that nitrogen. And so now the positive charge is sitting on that nitrogen atom. All right. If I go down to my other structure here, now I again have this positive charge located right next to that pair of that lone pair of electrons, so that can come down. Positive charge. All right, and so now we have this nitrogen with this positive charge, and it is allylic to this bond right here. But this cannot occur. Why not? Too many bonds on that nitrogen, right? Unlike a carbocation, which has only 6 electrons in its octet, this nitrogen cation here already has a complete octet. It's not accepting any more electrons. So these are the only 2 resonance structures that we can draw here. So then what do we think? What's our product going to be, C1 or C2? C1, more resonance structures, more stability. All right, so indeed we see this specificity in terms of where that incoming electrophile is going to be located. And because of this resonance argument here, we can see it's specifically going to be on that first carbon, that C1 position, which is more favorable than that C2 position. Cool. And I know this is really sad to hear, but that is it as far as new information goes. So let's just practice these reactions that we learned here today. We'll look a little bit more closely at some of them. All right. So in particular, let's do these nucleophilic aromatic substitution reactions. All right, so what if we want to convert this into the following? So importantly, just want to look at a few specific nucleophiles here, because when we introduce these nucleophilic aromatic substitution reactions, we just had it as generic nucleophile. Right? So now we're going to look at a few specific ones. Of course, the first step, though, in order to get rid of that NH2, I got to turn it into that good leaving group, that N2 leaving group. So in all of these, I'm going to start things off with the HNO2 and the sulfuric acid. All right, and then my second step, I'm just going to add in these different nucleophiles here. All right, if I'm trying to create phenol, I can add in that hydroxide leaving group. If I want to create a nitrile here, I can add in that cyanide ion. All right. And what about here? What can I do for a hydrogen? What are our it's got to be a nucleophile, right? So what are our nucleophilic hydrogens? Yeah, so lithium aluminum hydride or sodium borohydride, but our hydrides are our nucleophilic hydrogens. No. All right, so that would be a way to remove that aniline group and replace it with just a hydrogen. All right, so then let's say that again, if I'm starting with aniline here, how can I get to paranitroaniline? All right, if we just did our nitration reaction conditions as we learned about in that electrophilic aromatic substitution chapter, because it's such a strongly activated ring, we would end up getting nitro groups in all three possible orthopara positions. All right, so that wouldn't work for creating just the para-aniline. All right, so everybody take a second and see if you can't propose a path to get from A to B here. All right, so we have to add this protecting group on here. That will make it so that that nitrogen is no longer no longer basic or nucleophilic. We're going to use one of our more reactive carboxylic acid derivatives to do it, to turn this amine group into an amide group. Now, these amide groups are not strong activators. So if we do our nitration reaction, we'll get just that para product. And then we can remove that amide group, remove that carbonyl group by treating that amide with basic aqueous solution. All right, so again, we need to add on this protecting group here. All right, because then we can take that protecting group back off with that aqueous basic solution. All right, so then lastly, let's just practice one more here. All right, and for this one, we should have two organic products. I'm going to see the structure of both of those organic products. All right, remember that first step. You're going to fully methylate that nitrogen, creating that aminium ion with that positive charge. Our second step is when we have that elimination. All right, but we got to look and see where our elimination is going to occur. We're not looking at the carbon that's bound to the nitrogen itself, but its next door neighbors. These are the ones that are going to lose those hydrogens or potentially lose those hydrogens in these reactions. And we're looking specifically to which one is the least sterically hindered here. So I have a primary, a secondary, and a tertiary carbon. So which one is going to lose its hydrogen? The primary. So my alkene product here will be that 1 hexene. All right, and what's my other product? What's the functional group in my other product? So look, this 1, 2, 3, 4, 5, 6. That's these 1, 2, 3, 4, 5, 6 carbons. Everything else is going to go in my other product, right? So we'll also get a tertiary amine as our second product. And now it's got these 2 methyl groups on there because of that first step in my reaction. All right, and just by definition of how these reactions go, it's got to be a tertiary amine. Okay, so we'll always get an alkene and a tertiary amine as our products here. Cool? All right, awesome, congratulations. That is all the information I can spew at you here. I mean, that's good news. Bad news is that now it's the end of the semester and there's going to be the final and the 4th exam and all that other stuff, right? But in terms of making room in your brain for new information, we no longer have to do that.